So here's a funny question. This is kind of a conceptual question. Back in 13.3, there's a question called 113.
I come to this class victorious. I'll let you know that.
What'd you say?
I come to the class victorious.
Oh,
let you know that.
Victorious.
Yes.
From your
My
bout.
fight.
From
Yeah,
your
I
fight.
saw the hometown favorite, man. And they sold like 11,000 tickets. Man, I wanted me to die in the stadium. Whooped that ass.
And you beat him?
Spot is Mexican, yeah.
Wow.
Very mean Mexican.
Is he our home? He's Ocala's hometown
No,
favorite?
Sarasota.
Oh, down in Sarasota. Yeah. All right.
All right, let's start.
All right. All right. We'll keep following you. See what happens.
March 19th, the next one, I will be victorious as well.
All right. Heavyweight?
Yeah, heavyweight.
Yeah.
I'm fighting all the big black dudes and big Mexicans.
Yeah, good luck. Oh, boy. Okay, thank you for that. 113, where was I? In 13.3. It's, like I said, the title of the problem is Think About It. I don't think you have to do a lot of work, but you are supposed to think about it. It says, N is the number of applicants to a university. P is the charge for food and housing at the university, and T is the tuition. So hang on just a second. N is the number of applicants. P is the cost of food and housing, and T is the tuition. So at a university. And then what does it say? And it says this. It has this funny. It says, suppose that N is a function of P and T. The number of applicants is a function of the cost of food and housing and the tuition. And it says what information, and that dn dp is less than 0, dn dt is less than 0. What information is gained noticing that both partials are negative? Again, it's just a conceptual kind of question, but they just told me that dn dp is less than 0, and they told me that dn dt is less than 0, and their question is kind of funny. Their question is, what information is gained? So it's not that funny, and it's not that hard. What information is gained? I mean, what... Sometimes you can look at these derivatives and think of the word. I mean, one thing we've been doing is I've been talking about these derivatives as if we're on a surface and we're looking in a direction and we're talking about the slope of the surface in a certain direction. And this is slope of a surface, but that's a very geometrical thinking. I think this question is not geometrical. I think this question is more kind of conceptual and rate of change. So in other words, instead of thinking about the word slope, I want to think about the word rate of change. I think it's just the same thing, but a different way of thinking helps me here. And so, apparently, the rate of change of the number of applicants with respect to the cost of food and housing is less than 0, is negative. So does that mean I'm losing applicants? The number of applicants.
As the cost of food and tuition goes up, you lose applicants. It becomes less because it's negative.
Thank you. As the cost of food and housing increases a little, and it does increase a little, because if you remember, when we looked at these partial derivatives, when I would write with respect to x or with respect to y, you know, I would look down the positive x-axis and the positive y-axis. So he was correct in saying that that little change in P is an increase in the cost of food and housing. And with that little increase, apparently I'm getting a decrease in the number of applicants, because somehow this ratio becomes negative. This rate of change is negative. So it makes sense, I guess, The cost of food and housing goes up, and the number of applicants goes down. The rate of change is negative. Can you add one sentence to that, though? The cost of food and housing goes up, and the number of applicants goes down. That's why this is negative. Can you say something else, though, to add to that sentence?
After a certain risk.
After a certain limit, the number of applicants equals 0.
Yeah.
Both, and they have to both increase.
What's tuition doing in this circled statement? What's tuition doing?
Constant.
Thank you. I wanted to add that in there. I mean, that is part of what we've been studying. When we do take a partial derivative of n with respect to p, we are holding the other variables, like t, constant. So we had a good sentence going there, but I wanted to add the phrase, when you hold tuition constant, I wanted to add that phrase to this. When you hold tuition constant and let the cost of food and housing go up a little, the number of applicants decreases. I'm going to add, can we say this sentence? I think this sentence says, when you hold cost of food and housing constant and let the tuition rise a little bit, what happens to our number of applicants? It decreases again. That's all. We're done. It was just putting some meaning onto these variables. These variables mean something, and so these mathematical statements might mean something. And the rate of change is negative, but you are holding the other variable constant. I wanted to get that in there. That's all. Let's do another problem. Here's a 116. I'm in 13.3, and here's 116. This is actually more actual work involved. That was just something to talk and think about. Hey, the measure of how hot weather feels to an average person is called the apparent temperature index. And this is the formula for it. The apparent temperature index is A, and it equals this. 0.885 T minus 22.4 H, 0.885 T minus 22.4 H, plus 1.20 TH minus 0.544, plus 1.20 TH minus, what did I say, 0.544. Wow, okay. This is a model for what we call the apparent temperature, or how the temperature feels. The apparent temperature. That's interesting. And what's going on? That's the apparent temperature. What are these other variables? Well, if I read, they'll tell me. T is the air temperature. Okay, T is the air temperature. And H is the relative humidity in a decimal. Okay. So that's what T is. T is the kind of the actual temperature or air temperature, and H is the humidity. Okay. So apparent temperature must depend on these two variables, I guess. The way a temperature feels depends on these two variables. What would they like me to do? They want me to find dA dt and dA dH at the moment when T is 30 and H is 0.80. Okay. All right. So at the moment when T is 30, and that's in Celsius, I think, and H is 0.80. Okay. Plug it in and find the apparent temperature. No, that's not what they asked. That would be interesting, though. Plug it in and see what it feels like, man. Yeah, actually, they just wanted the rates of change. They wanted this dA dt. And they wanted dA dH. Yeah, that should be easy, I suppose, you guys. Can you guys handle these easy partial derivatives?
Yeah.
I hope so. dA dt is
0.885
0.885
plus 1.20H
plus 1.20H. That's how you take a derivative with respect to T, isn't it? Yeah, he's right. Pretty easy. Let's do the derivative with respect to H. With respect to H, I guess it would be negative 22.4 You guys agree? And 1 plus 1.20 t. Okay. Now, let's plug in these numbers and see what's going on. If I plug in 30 for t and 0.80 for h, I might want a little help, but I'm plugging these in here. And I wonder what I get. For the 80t, when h is a 0.80, that's my plugging it in. My calculator's working. 0.80.
1.845.
1.845. Huh. And what about if you plug in a 30 right here?
13.6.
13.6. Wow. Again, this question, the next part of this question probably says, what the hell does all these numbers mean? Can you think about it, and can you put some words into this scenario? What do those numbers mean? I think. Let's see. What do they ask? Oh, here's their question. Which has a greater effect on your apparent temperature? Which one has a greater effect? Air temperature or humidity? Which one has a greater effect?
Humidity.
Really? Because when you hold the humidity constant and let the air temperature vary a little bit, how does it affect the apparent temperature? Just by about 1.845 degrees. But when you hold the air temperature constant and let the humidity vary, how does that affect the apparent temperature? Wow, 13.6 degrees. So which one has a greater effect on the feel? Humidity. Maybe you just knew that because you grew up in Florida and you heard that your whole damn life. Or that's what they say out in Arizona. They say, it's 120 degrees. Oh yeah, but it's okay. It's a dry heat. They don't have humidity.
Yeah.
So it feels better. 120 feels better. Anyway, good. I guess humidity affects this apparent temperature more than air temperature. Yeah.
Is that why we needed the partial derivatives? Find which one affected more.
I mean, that's what they're teaching me. They're teaching me that if you hold one of them constant and look at the rate of change with respect to one variable, and then look at the rate of change with respect to the other variable, holding the other one constant, it's a much greater change. Yeah, right. Okay. I got some more problems in mind. I assigned 117, and I actually assigned both of these, and then I just walked in and did them. So I might have spoiled all your fun, but I won't spoil all your fun. I won't do every problem. Did you happen to wander in here with any requests or questions? You know, I did a lot in 13.4. These are both from 13.3. I did some of those cool error word problems in 13.4. Did you want me to help you with any of those? Did you try any? Okay. You don't have to. Maybe by Friday, we're taking a quiz, so maybe by Friday you should try a few. But I don't want to do more of those today, so I'm moving on. I'm flipping the pages. I'm going to 13.6, which is where all the good stuff is. I'll quickly remind you of this. In 13.6, we had this lecture Friday, but we learned how to find what we call the duff. And it is just this fx times u1 plus fy times u2. Basically, it's the slope of the surface. Let me add this, though. In the direction of the unit vector u. In the direction of this unit vector u. So it's the slope in any direction we want. It usually I got some kind of a unit vector to help me find the direction of the slope they want. We also, real quickly, these are just notes. I mean, this is, I already gave you this. This is called the gradient. And it was a vector. The gradient is a vector. F partial derivative with respect to x, comma, f partial derivative with respect to y. It happens to be, I'm going to say it's a vector that points in the direction of maximum slope. This was Friday's discussion, that points in the direction of max slope. See, you're standing on this, I mean, you're on this surface, and I can ask you for all these different slopes. I can ask you for the slope in that direction, the slope in that direction, the slope in that direction. That's what all these duffs would be. Give me this duff, give me this duff, give me this duff, I can ask you for all these slopes. Anyway, one of those directions, that direction, is the one that points, is the one with the maximum slope. That's the one with the maximum duff, is that direction. And the value of that slope, the actual maximum slope, is his magnitude. His magnitude is the maximum slope. So so when you use the word gradient, be a little bit careful. I mean, I think it's used loosely sometimes amongst maybe books and professors and students, but to me there's two things. To me, the vector is the gradient, and the magnitude of that vector is the maximum slope. I mean, I don't know, but I think the use of the word gradient is the vector, or the direction, which is the direction of maximum slope. The magnitude of that gradient is the maximum slope. Just so. Hey, by the way, I don't think I mentioned this Friday, but there's a couple things I didn't mention Friday. That's why, but I did mention all that. A few more things need to be mentioned here in 13.6. One of them is, here's a slight alternative form here to this duff. There's my formula for duff. By the way, you need to know these kind of formulas and this terminology and this stuff. You need to kind of memorize it, I guess. But watch this. Here's a different alternative formula for duff. You could say that the duff is, here I'll write it like this, the duff is this. You could say it's the gradient dot product the unit vector. Does that make any sense to you? Mm-hmm. I mean, if you took this gradient, see here it is, by the way, and dot producted this unit vector, which tells you the direction you're looking in for your directional derivative. That's what this is. But if you dot producted these guys, don't you have that formula right there? Right? Dot producting. Yeah. So, whatever. Here's the other funny thing about the gradient. I want to say, I guess I'll just say it, and then we'll do a problem to sort of illustrate it. But this is a true fact about the gradient I didn't get to Friday. The gradient is this vector, and here's it. It is always, I want to say, it is always normal to the level curves of the surface. It's normal to the level curves of the surface. By the way, when I say normal, I mean perpendicular. Right, perpendicular. It's normal to the level curves of the surface. It's a true fact. We need that fact. It's an important fact. Like I said, maybe I can illustrate it for you if I do a problem. Hang on just a second. Let's just think about it conceptually a second. Watch this. If I had a mountain like this, see this beautiful mountain? See it? Mm-hmm. If I looked down on it and I was looking at the level curves, I'm suggesting that maybe these level curves are circles. So I don't know. Maybe you can. Is that okay with you?
Yeah.
And so here's this level curve. There's another level curve. Here's another level curve. Which ones are higher, do you think?
The higher ones?
Yeah, I mean, yeah, which ones are the higher
The
ones?
middle, the small.
The interior ones, yeah, thank you, right, right. The interior ones are the higher part of the mountain. So maybe I label these, remember these are labeled with C values, and those C values are really Z values, which are really height. So I'm just going to make up, maybe that's 10, maybe that's 8, maybe that's 6, maybe that's 4. You know, if you were like walking around on this level curve, now I mean, here's a question. If you wanted to, you're walking around on this mountain, and if you wanted to, you're messing around, walking around on this mountain. If you wanted to remain at your current elevation and not increase in Z or decrease in Z, but remain at your current Z, which direction would you travel? Here you are right now. What would you do?
Along the line?
You would try to stay on this level curve. Remember, this level curve, this C value of 4 is a Z value. And to remain at a height of 4, you should just follow this path. Just be going around and around the mountain. But you won't be climbing it or descending it. You'll just be staying at a height of 4. The level curves is a picture of a constant height, so to speak, or a constant Z value, which I'm interpreting as height of a mountain. So are you with me? If I wanted to remain at my current elevation, I should head off in this direction or head off in that direction. That would be a tangent line to this curve. You okay? What does this say? The gradient. The gradient is not tangent to the level curves. It says the gradient, I didn't just draw the gradient. No, I didn't. Hang on. The gradient is normal to the level curves. Because what does the gradient do? The gradient points in the direction of maximum slope, which again, back to the mountain climber, that would be, if I'm a mountain climber that wants to challenge myself and go up this mountain the steepest goddamn way I can, I should do this. I should follow the gradient. The gradient takes me up the steepest direction, which would be
towards the center of this picture.
exactly toward the center, I think. But the point is, it should be perpendicular to the level curves. It's supposed to be perpendicular to the level curves, or perpendicular to the concept of not changing your height. Huh. Yeah, I guess it's this. The direction of no change in height is following the level curves, and the direction of maximum increase in height is perpendicular to that. The direction of steepest ascent is perpendicular to the direction of no ascent, apparently. Always, apparently. Because the direction of steepest ascent is your gradient. It's always normal to the level curves, which are always the direction of zero change in height. By the way, what if I wanted to climb down the mountain at the steepest rate? Down. This vector, this gradient, points in the direction of maximum slope. How do I go down the mountain at the steepest descent? This is the steepest ascent. What would be the steepest descent?
Opposite.
The exact opposite of this, right. And I did say that Friday, but it's not up here yet, but I could put it up here. Right, the negative of this. Right, the opposite of that direction is a vector that points in the direction of minimum slope. Good, those are good questions. Let's do a problem. I think I'll do this. I found a problem in 13.6. There's a lot of good stuff on your way to this, but I found this one. This is kind of tricky. 46. So I'm in 13.6. I'm going to try this problem 46. You guys might be able to learn something from it. It's kind of tough though. It's got this function f of xy equals 8y over 1 plus x squared plus y squared. All right, so then this is 46 out of your book in 13.6. So then here's what it does. It says, analytically verify that the level curve at c equals 2 is a circle. Okay, so they want me to work on the level curve when c equals 2. All right, so, and by the way, they told me it's a circle. They want me to verify that. I'll just do that, I guess. So how do I draw a level curve? That's back in 13.1. We practiced it a little. To draw this level curve, I take this c value and I insert it for this z value here. And this z becomes a 2. And now, you know, once you've inserted a value for z, then you've got a two-dimensional system here that you could try to draw. You can try to draw this two-dimensional thing. They suggested it was a circle. If I'm going to draw it, I got a little bit of work cut out for me here. I'm going to multiply both sides by this. Hey, after I multiply by this, I'm going to also then, the next thing I'm going to do is divide by 2. So this will become 4y. How are you guys doing? Now I'm going to write this like this. Watch this. X squared plus y squared. I'm going to move the 4y over. I'm going to leave a space. Equals. I'm going to put the 1 over on the other side. You guys okay? You can do algebra? All right. I'm doing a little algebra. But now I'm going to complete the square. I'm going to complete the square. What number should I add right here?
4.
I should add a 4. If I add a 4, I should go over across the equal sign. I should also add a 4. Now I have x squared plus y minus 2 squared equals a 3. Yeah, guess what? I've done what they asked. They said when you sketch this level curve, it ought to be a circle. Well, that is a circle. What's the center of that circle?
0, 2.
0, 2. And that's good. And what is the
Square root of 3.
radius of the circle? Square root of 3. Good. I like that. Reading my mind. I'm going to draw that guy here. It's centered at 0, 2. That's 2. It's centered at 0, 2. But it's got a radius of the square root of 3, which is about 1.7. That's it. I'm going to label this c equals 2. It's a level curve when c equals 2 for this surface. For whatever this surface is. This is his level curve at c equals 2. All right. Let's see what else they asked me. At the point, square root of 3, 2. Let's see, hang on, where is that point? Square root of 3, 2. Oh, if I go over the square root of 3, that's about right there, 1.7, and then go up 2. Oh, I think that's right there. Are you okay, guys?
Mm-hmm.
Square root of 3, over, and then up 2. That's that point. Square root of 3, 2. There's a 3D surface, but I'm only looking at the 2D level curve when z equals 2, and that point is on that level curve. Okay, let's see what else they asked me. Oh, at the point on the level curve, sketch the vector that shows the direction of greatest increase of the function. What kind of vector do you think that is?
Normal.
Okay, good. You think it'll be perpendicular to the level curve?
Yeah.
Because what they just described, they didn't use the word, but they just described the gradient. Thank you. How did they describe it? They didn't say gradient, but they said, sketch the vector that shows the direction of greatest rate of increase. Yeah, that's the direction of maximum slope. Greatest rate of increase is a different way of saying that. Yeah. So they want me to sketch the gradient. And you're saying it's probably perpendicular. You're good. Hey, it probably is perpendicular. That means it's either pointing there or it could be pointing out. Yeah, I'm not sure, I guess. Maybe I should actually go find the gradient. How do I find the gradient? I guess I erased some of my notes. It's a vector, and it's easy. It's the partial derivative with respect to x, comma, partial derivative with respect to y. I need to do a couple partial derivatives. And this, yeah, you guys, I need to do a couple partial derivatives. I like this problem. I like quotient rules. This is a quotient rule, I think. Although for x, I could kind of avoid the quotient rule to tell you the truth for this x, but let's just do it. Quotient rule. Derivative of the top with respect to x. 0. Times the bottom minus, write down the top, and take the derivative of the bottom with respect to x. Derivative of the bottom with respect to x? 2x, thank you. All over the bottom squared. Are you guys okay? I just did a quick little quotient rule to do the partial derivative with respect to x. I'll clean it up, but let's do the partial derivative with respect to y. That really requires a quotient rule. The derivative of the top with respect to y, 8, times the bottom, minus, write down the numerator, and take the derivative of the denominator with respect to y. 2y. All over the denominator squared. Wow, this is cool. These two partial derivatives there they are. They're kind of nasty, but they were doable. I can kind of try to clean them up just a tad. This fx is just easy. It's just a negative 16xy over that denominator. I would never FOIL out that denominator. I don't think there's ever a reason to do that. And in this one, I guess I would distribute the 8, try to collect a few like terms. I'm going to do some of that in my head. I think I get 8 plus 8x squared. I'm going to get 8y squared minus 16y squared, so I'm going to get a negative 8y squared. That's that numerator all over this denominator. How you guys doing? Okay. You know, what I've just calculated is the gradient in general. Again, what I have is the gradient, which is a vector, and I have it for any point, x, y. It is this vector. I really don't want to make you write down too much stuff, but here it is again. This thing written in this form, comma, what a pain, right? A lot of writing, but that's it. In general, that's my gradient. What I'm really trying to do is find this gradient at this point. What point? What point? What point? What point? What point? That point, that's right. That point right there, the square root of 3, 2. You're right. Let's try that. I want the gradient evaluated at the point square root of 3, comma 2. So I should plug those in. I'm going to kind of do that up here if you don't mind. If I plug in that point square root of 3, 2 for x and y, I think I get negative 16, wait a minute, y is 2, negative 32 square roots of 3. All over, this is fun, plug in a square root of 3 and a 2 right here. Square root of 3 squared, that's going to be a 3, that's a 4. 4 plus 3 plus 1, I think that's 8 squared, I think that's 64. Plugging in the square root of 3 and 2, sorry. You know, part of this class is beautiful concepts and beautiful discussions. And then part of this class is nitty-gritty, get busy. get to work, plug in some points, do some math. It is math class. We can't avoid cranking out some math. We can't avoid cranking out a few quotient rules in Cal 3. Cool. I'm going to write that here. That's specifically, that's a negative square root of 3 over 2. What is Fy evaluated at that point? What did you say?
0.
Yeah, well, I know the denominator is 64 because I already did that denominator. And you just said it's a 0 in the numerator, huh? Square root of 3 squared is a 324. That's 32 minus 32. X is a square root of 3, y is a 2. Yeah, you're right. That's a 0. Awesome.
Well, that makes sense.
Oh, it does make sense. Yeah, can I draw that little vector? At this point, on my level curve, remember we said he should look like he's perpendicular, and god dang it, he is. Now, on this level curve, at this point, the gradient came out to be that. If you draw that, it's that. You guys, I like these things drawn kind of accurately, so I did draw that length accurately. The radius was the square root of 3, and then that distance was square root of 3 over 2. So I just, that's him. That's the gradient. That's awesome. Just verifies all that stuff I told you about being normal to the level curve at any point. It'd be true at any point. If you were at this point, you should have a gradient that looks like that. If you're at this point, you should be normal to the level curve. Is there more to this problem? Let me see. On the level, at that point, square root of 3, 2, on the level curve, they also want me to sketch a vector that sketch a vector such that the directional derivative is 0. Again, this is kind of new language for us, but that directional derivative was the duff. The duff is the slope. The directional derivative is the slope. They want me to sketch a vector that shows me where the slope is 0. Okay, good. This totally coincides with this discussion we had 10, 15 minutes ago. The direction where the slope is 0 would be the direction where you don't want to increase or decrease at all. That would mean follow the level curve or be tangent to the level curve. I mean, they specify the direction by drawing this vector. That's tangent to the level curve, or this vector. Of course, once you take a step or two, you should redo your calculations and follow the level curve is really what you want to do, right? But at this moment, at this time, the direction you should head is tangent to that level curve, right? For a slope of 0. For steepest ascent, follow the gradient. For steepest descent, go the negative, the opposite of the gradient. Yep. Cool. That was a cool problem. And this last cool concept that I didn't get out Friday that is now out. Okay. All right, listen. This always gets a little tricky, but I'm going to try to get another concept out here for you. You know, when I jumped from 13.4 to 13.6, I skipped this 13.5, and, well, it isn't exactly 13.5. Anyway, hang on. I got to get another concept out here to you. See, what I want to do is I want to take this whole idea and jump it up a dimension. So let's see if we can think our way through this. When we have z equals a function of x's and y's, right? Okay, so you guys can see this. You know that you got three variables there. There they are, three variables. Z is by itself. It equals a function of x's and y's. And that's a nice 3D surface. Okay, that's a nice 3D surface. You know, his level curves are called level curves because they are two-dimensional. Do you agree with that? Two-dimensional level curves. And that happens when you plug in a C value for Z, and you plug in a number for Z, and you get this two-dimensional level curve. And then what did we just have this big discussion of how the gradient, and by the way, the gradient is a 2D vector. It is fx, fy, so it's easily drawn in two dimensions, and when you draw it, it's perpendicular to this level curve. This is all, so this drawing is all in 2D. When you draw the level curve and you draw the gradient, this is all a two-dimensional drawing, and this gradient is, I'll say it again, normal to the level curve. Okay, good. All right, so what if we jack this all up one dimension? What is this? Okay, what does that mean? I'm jacking it up a dimension. Oh my God. All right, so now we're saying I might have W, which equals some capital F of X, Y, and Z. Are you with me? I'm writing a capital F on purpose here. Right? Look at me. Now I got a three-dimensional input. I got this fourth variable. I mean, technically, this is some four-dimensional surface. 4D, I don't even want to use the damn word surface. 4D, something.
Make up a word.
Yeah, make up a word.
Four-dimensional universe.
It's 4D. Now hang on. It's 4D. If I plug a number in for W, like I mean, isn't that how you find the level curves? You plug in a number for Z and then it's two-dimensional. Well, if I plug in a number for W, and I'm going to try this number, W equals 0. And then I get 0 equals big capital F of X, Y, Z. I mean, now, it was four-dimensional, but when I plug a number in for W, now it's a three-dimensional, and it's a very specific one. When W is 0, this is a 3D level surface, three-dimensional level surface. Are you guys okay? Mm-hmm. All right, now what you haven't seen yet is this gradient. With the capital F, I'm dealing with three variables. With the capital F, this is a 3D gradient. It's different than this classic gradient back here. This is a 3D. It's big capital F with respect to X, comma, big capital F with respect to Y, comma, big capital F with respect to Z. It's the partial derivative with X, Y, and Z, and it's the 3D gradient. So now this is a 3D vector in space. And guess what? The 2D gradient is normal to the 2D level curves. The 3D gradient is normal to the 3D level surfaces. Okay, awesome. Awesome. Now hold on. This is normal to this big capital F of X, Y, Z, which is a surface, which is a level surface. I mean, are you with me? This is a surface now, you guys. This is some kind of surface. And at this point, I've got this kind of gradient. It's sticking out 3D, level to the surface. different gradient. Don't get confused. Don't. It's different. We've jumped up a dimension. But see, we never really, we play this game, but we don't ever really go into 4D. We hijack this notation to serve our 3D purposes. That was well put, by the way. Listen. This is a surface, and by the way, this is a surface. Three variables, it's a surface, and by the way, you should know what it is. It's a nice, classic, easy, cool surface that we've studied.
That is a elliptic parabola.
It is a paraboloid. This is a
Paraboloid.
classic, beautiful paraboloid. Sits at the origin, opens up, nice and circular. In general, they're elliptic paraboloids, but this one's nice and circular paraboloid. Anyway, that's what he is. Now, can you please write him with the small f notation? What would you do? How would you write him with the small f notation? You would just replace z with, do you understand me?
Oh, yeah.
Here he is using the small f notation. F of xy is just z. It's just another name. We've been talking like that. But here's what I'm suggesting. Can we express him with our big F notation? Now, what's our big F notation? Our big F notation maybe implies that it equals some fourth variable. Yeah, but then the key was, look what we did to that. We let w equal 0. We let w equal 0, and then we don't have a 4D thing. What we have when you let w equal 0 is we have a 3D thing. And the way this is, the notation for this big F is that it does equal 0, which means all the x's, y's, and z's are on one side of the equation and it equals 0. When you get all your x's, y's, and z's on one side of the equation and it equals 0, that's what you call big F. It's the same surface we're talking about here with our little f notation. Little f is z. I'm saying move the z over, make this equal to 0, and we call that big F. Big F of x, y, and z is, listen now, when I use this big F, it's not really going to be equal to w. I did that to do the analogy. But really, when we use the big F notation, we're letting it equal 0. So when this equals 0, I can call it big F. And what is it? It's x squared plus y squared minus z. It's the same damn thing. These are both the same. These are the same. Same. Boy, that was tough. What's my point? My point is that there's these two kinds of gradients. See, if you want to, when I say do a 2D gradient, or if I ask you about this guy, I mean, that's just our good old 2D gradient. I should refer to the little f notation, and I should draw that gradient. It's easy to do. Partial derivative with respect to x, 2x. Partial derivative with respect to y, 2y. So, and it's a two-dimensional, and it's perpendicular to the two-dimensional level curves of this guy, okay? But there's this new thing called this three-dimensional gradient. Let's just calculate him, please, off of this. This three-dimensional gradient. What is it? Similar, it's 2x, comma, 2y, comma, negative 1 in this case. And he's not perpendicular to the level curves. He's not two-dimensional. He's three-dimensional. You know what he is? What is he?
Perpendicular to the level surface.
Thank you. He's perpendicular to what we call the level surface up here. But now I think I just want to call that the surface. I mean, this is just a surface. but I'm expressing this surface two ways. I'm expressing it this way, and I'm expressing it this way. This is the same surface. Because this is not really a W. When I'm used the big F, it's not really a W. What is it? It's a 0. So I'm not really adding a dimension to it. It was just a trick. For a second I did, just to get you to digest this. Then forget that. I'm not really going into 4 dimensions. I'm just expressing 3 dimensions in a different notation. I can express 3 dimensions like this, where Z equals X's and Y's, or I can get all the X's and Y's and Z's on one side equal to 0. I can express it like that. But when I express it like that, it gives rise to this thing, the 3-dimensional gradient, which is perpendicular to the damn surface itself. Perpendicular to the surface. I better say that. Perpendicular or normal, or perpendicular to the surface. Why do we care about that? Why is that so important? Because if I find this normal vector that's perpendicular to the surface, you know what I'm after. This should remind you of chapter 11. If it's perpendicular to the surface, then if there's a plane right there, if there's a tangent plane right there, it's perpendicular to the tangent plane. And if you remember from chapter 11, the key to finding the equation of a plane was finding a normal vector. We needed that normal vector, and then we would get the equation of the tangent. Well, we didn't call it tangent plane. To get the equation of a plane, we needed a normal vector. And that's what he is. If I want a tangent plane, this is how you get this. Then I got the normal to a tangent plane. Right, that's this. This is the key to the whole thing. Right, so now I'm up into 13.7. That was tough, man. Every semester that's tough. Hopefully you got it. If you don't, watch it again. But it's a tough explanation. It's this analogy. You jump up into this 4D thing kind of temporarily and think this through like this. The book has good explanations. The book has good pictures. But what just happened is we kind of eased up here into 13.7, where the classic question is not a very difficult topic. We can find the equation of a tangent plane. And I'm just going to remind you that the equation of a plane, do me a favor, don't write this down. Well, do me a favor, yeah, don't write this down. The equation of a tangent plane was A, x minus x naught, bless you, B, y minus y naught, and C, z minus z naught. This was the equation of any old plane back in chapter 11. Hang on a second. And then that A, B, and C was my normal vector, right, you guys? Okay, well, hang on. Let's erase the A, B, and C. And with regards to a tangent plane to a surface in 3D, that A, B, and C are going to become this capital Fx, capital Fy, capital Fz. Exactly. Let's put that in there. Capital F subscript x, capital F subscript y, capital F subscript z. That's my normal vector to the surface. Therefore, it's normal to this tangent plane. And I just refer to it as a normal vector here, but we call it this. It's this 3D gradient. It's with that capital F notation. It's that 3D gradient.
Can I write that down?
Okay, now you can write this down. Yeah, thank you. I just temporarily wanted to throw the A, B's, and C's in there to make that connection. But yeah, now, write this down. Yeah. Can I write this down? All right, cool. Let's just try one of these before we leave. I want to find, I like right classic question. Find the equation of the tangent plane find the equation of the tangent plane to this surface. Now here comes a surface. X squared y cubed z to the fourth equals 13. Hang on. Hang on. Don't look up here. Are you guys looking? Don't look. Thirteen z minus 5. Find the equation of the tangent plane to this surface. Wow, look at this crazy surface. See it? And I want to do this at the point -1, 2, 1, which I hope is on that surface. If I plug those numbers in, it should be on that. At that point is on that surface. So I want the equation of a tangent plane. If I want the equation of a tangent plane, they better give me a point. Did they give me a point? Mm-hmm. Yeah, they gave me a point. The point goes right here. That's your x naught, y naught, z naught. Okay, what else do I need? I need this normal vector. The normal vector is the 3D gradient. That's what I need. To get a 3D gradient, I need to understand what big F is. What is big F? When you get all that crap over on one side and get it equal to 0, that's big F. Big F is when you get all the x's, y's, and z's on one side and get it equal to 0. You call that big F. It's not really supposed to be a 4-dimensional thing. It's just a rewrite of a 3-dimensional thing. So that's easy enough. Big F would be, just get off, x squared y cubed z to the fourth minus 13z plus 5. Is that okay? I moved everything over. Technically it equals 0, but I don't call it 0. I call it big F. Yeah. Awesome. Now I just need my damn 3 partials. Are you guys okay? Mm-hmm. Okay, cool.
Better, okay.
Good. All right, good. Let's do big FX.
2x y cubed z to the fourth.
Great. Thank you. 2x y cubed z to the fourth. He's right. That's how you would do it. That's good. He's right. All right, big Fy.
X squared. Or 3x squared y squared z to the fourth.
3x squared y squared. 3x squared y squared z to the fourth. That's it for Fy. You're right. And big FZ. Big FZ.
4x squared y cubed.
4x squared y cubed z
Cubed. Minus 13.
minus 13. Woohoo! This is fun. All right, I guess we got to evaluate all those at our point. Let's evaluate all these at -1, 2, 1. Okay, let's evaluate all these at that point. -1, 2, 1. That shouldn't be too hard. -1, 2, 1. I think I got a -16 on that first one. I think I got a 12 on the next one. $19 on this next one. 19, I think. Ta-da! This is awesome. I mean, I can write that as a 3D vector, but really all I don't know. I want the equation of the tangent plane. I really just wanted those 3 numbers. I'm ready to write my answer. My answer is -16 x minus -1 plus 12 y minus 2 plus 19 z minus 1. What would be awesome is to find some cool computer program, type this surface in there, and then type this in there, And you should be able to see a nice tangent plane to some kind of crazy surface. But need some cool 3D graphing software to do that. I'll just finish cleaning this up. Are you guys okay? That's my normal vector. I've got this normal vector and a point now. Yeah. That's x plus 1. I'll just clean this up. Negative 16 is 12y minus 24. 19z minus 19 equals 0. Negative 16x plus 12y plus 19z equals, everybody knows that's 59. Woohoo! That's it. My tangent plane to this weird surface at this point. That's pretty cool. I'm going to add one thing. I like this. Find the equation of a tangent plane. I kind of like this question. You should practice some of it. I just made this one up. The book's probably got nicer questions. The key is understanding big F. So I think you got it. I've tried to explain what this big F notation means as opposed to the little f notation. One little thing they add to this, sometimes they want one more thing. They want the normal line. The normal line. Well, okay, so hang on a second. We got a surface, that's a surface, at a point, we just found the tangent plane. What we have is this normal vector called the 3D gradient is the normal vector. But they want a normal line. A normal line would be a line. I mean, a line in space, an infinite line in space. So we discussed how to write equations of lines in space. That was chapter 11. We would write parametric equations. We would write x, y, z, and what we would write is a point that's on the line. Can you tell me a point that's on this line? Negative 1, 2, 1. I'm going to put negative 1, 2, 1 right here. And then do you remember what else we would have? We would have a parallel vector. We had AT, BT, CT. We would write these parametrically, and we would need a parallel vector. Well, who acts like my parallel vector?
16, 12, 19.
Thank you. That gradient is right. If we're calling this line a normal line, it's perpendicular to the surface. The gradient is perpendicular to the surface. The gradient is parallel to my line, and so I just use those numbers. Yes, yes, yes. Are you guys okay? Does that? So sometimes they ask for the equation of the normal line. I'm more of a fan of the equation of the tangent plane, but we can do this. It's easy. One more easy step. By the way, just for fun, how would you write that line with our vector valued notation that we've learned about? How would you write that?
It would be you said it would equal to, so
there's my x.
and then you would have y minus 2.
There's my y. No.
Oh,
And there's my z.
and parametric.
Just, yeah, I mean, those are parametric equations. That's how we were, in chapter 11, we learned how to write a line with parametric equations. In chapter 12, our parametric equations turned into vector valued functions. And so this is synonymous. But we did helixes and we did some stuff. We never did lines too often. But that would be a line in space. Right. Okay, you know what? I think I quit. You have a new teacher Wednesday. No, I didn't mean that kind of quit. I'll just quit today. I will see you Wednesday.
Don't quit.
I will see you Wednesday.